teaching, so I just kind of forget. It's like, oh, forgot to take roll. All right. So first thing first, I have scheduled our first exam to be on the 28th of September. So this is based on how many, what topics I want to have covered by the time we have the first exam. So it's 2 weeks out. Okay. What we'll do is I'm going to finish, all the comparison topics, which we're not going to talk about today. That's going to be next Monday. So on next Wednesday, I will give you a practice exam. I can give you the practice exam earlier, like next Monday, so you guys can kind of chew on it, and try to figure out, the answers. Um, this is going to be a paper-based exam, so we are not going to use any electronics. So for those of you who have been taking notes using an electronic, device, you might want to print out, some of those notes. I would advise you not to print out everything, just kind of consolidate your notes in a much more easy to read and easy to search manner, and then print that out, okay? So I will not have an upper limit of what you can bring with you. Like some of the other classes, they say 1 page, right? Nope, you have no limitation as to, how many pages you can bring with you. But the more you bring with you, the harder it is to find something. Okay, so that's the trade-off. And that's why, from day one, I have been telling you guys to do what? Put all the definitions, put all the symbols, put all the, key concepts on, at one single place. So it's easy to look up. Okay, so you might want to start to collect, those definitions and symbols and whatnot that you will find, helpful in the exam. So that's the first thing. Second thing is today is the first day of IBM Z Day. Um, and the Z has nothing to do with zombie, Z Nation, etc. So IBM Z Day is a 2-day conference starting today. Actually, it has started already. It started at 9 a.m. Pacific Standard Time. So it's basically IBM trying to let the world know about their products. From your perspective, IBM Z Day is an opportunity to learn about what they call enterprise computing. Enterprise computing is not usually discussed, and I would say most UCs and CSU professors, kind of frown on, what we call enterprise, computing, because they use mainframe computers that can trace the root all the way to the 60s, like early 60s. So most universities, would look at mainframes and enterprise computing as something that stuff is in the past. But if you go to Wells Fargo Bank, if you go to American Express, Walmart, Raley's, the supermarket chain, the state of California, they will say, oh, we are in need of people who know how to work with enterprise computing, particularly the IBM, mainframe computers. Because, people who wrote those programs in the 60s, many have passed away, many have died already. So it's not like, they can come back even as a consultant anymore. Yeah, it's that bad. Okay, it is that bad. So the state of California actually has a need to replace, the people that they have lost, and so far I think it is not even breaking even. So they are still losing people overall speaking. So that means from your perspective as a student now, if you look into enterprise computing, you go like, oh, this stuff I can do, okay? I can master, I'll talk about this in just a little bit. I can master the techniques and the programming language and so on. You have just opened up a new possibility for your career. Now, just because you get into the state, government, because you know about mainframe stuff, doesn't mean you have to be doing mainframe stuff until you retire. Okay, because the state government has a lot of possibilities of transferring lateral, keeping the same position, the same pay, or also advancing your position to at a higher salary. So I would definitely advise anyone who want to understand more possibilities to attend Z Day. I'll be one of the panelists later on today at 5 p.m. Pacific Standard Time. So whether I'm there or not is not important. the important part is it's going to be a panel, it's going to be a discussion. So if you guys have any questions, especially if you participate even earlier, and you have some questions, we will have panelists to try to answer those questions. So just an extra opportunity. I am not paid by IBM in any way, but I do want to make sure that you guys understand that there is this possibility, there's this opportunity. And if you don't like enterprise computing, you think your COBOL programming is the dumbest thing ever in history, that's okay too. Okay, don't get into enterprise computing. I'm just telling you guys that there's a possibility. So there's that. I'm making sure that I'm recording because on the other day in CISP310, I accidentally stopped recording. So I ended up having to make up for the recording just to be fair. All right, so there is that. And I think we are ready now to tackle what we are here today for. And this is also great. It's called a vertical tab because now I can quite easily see which tab is which tab, and I can just go ahead and click on the right one. So we are now talking about signed versus unsigned numbers. That's going to be the main topic for today. All right, so the first thing is, if you ask your math professor, and you ask, so how many integers are there? The math professor will look back at you and go like, there's an infinite number of integers. Because if you just tell me that this here is the largest integer, then your math professor will ask, what about this number plus 1? You go like, right? But in computer science, when you use int or unsigned in C++, you don't have that luxury. There's a finite number of integer values that can be represented by an int. Okay, so that's one major difference between what we understand integers are in a math class as opposed to what integers are in this class or in any programming class. So I'm just going to read the sentences one by one and try to make sure that we all understand what the sentences are actually trying to convey. So that's basically addressed the first paragraph. And then the second paragraph says, based on the discussion of how values are represented by numbers in module 0282, remember that sigma notation, V equals sigma, and then the I is the digit position from negative infinity to positive infinity. And then we have D of I, which is digit I, times whatever the base is to the power of I. Okay, yes, I do remember that equation, but that equation will give you the value. So a base 2 number with digit 0 to w minus 1, and therefore a total of w digits, w is an integer that is at least 1, can represent values from 0 to 2 to the power of w minus 1. So now we have a range if we choose to represent unsigned integers, okay? This is the range of an unsigned integer if w is the width of the integer. The smallest integer you can practically have in C and C++ is a char. So most of you will say, but the char is not an integer. It is an integer. It's just a very short one. It has a width of 8. But char by itself is signed. So if you want to look at char as unsigned, you have to say unsigned char. So an unsigned char, which is 8-bit wide, can represent values from 0 to 255, because 2 to the power of 8 is 256, and we have to remember to subtract 1 from it. We have to subtract 1 because 0 is taking one of the spots. So that's why we cannot go all the way up to 256. We can only go up to 255. But in our examples, in this entire module, I am going to fix the width to 4. Just because it doesn't make any sense to use that many bits, because it just makes the table much bigger without any actual benefits. So the next question is, how about the other integer values? If we're looking at a 4-bit wide integer, which should only be able to represent 0 to 15, what about 19? That seems to be a very silly question. So there are two ways to look at the question of how 19 is represented as a 4-bit integer. The first one is simply to say 19 cannot be represented as a 4-bit integer, which is the correct answer in most cases. This interpretation is relevant and useful in most cases. I have to give you an example of why the width of integers is really important. I used to teach a robotics class at UC Davis, as a adjunct, and the class, was taught to write what we call motion control, software or algorithms. So we want to ramp up the velocity of a stepper motor, let it stay constant for a while, and then ramp it down in order to travel a known number of steps. So in the math of doing all of that stuff, we have a lot of integer variables. So I told the students, okay, you might want to test all of this stuff here, quote unquote, dry, using a simulation. So you can just basically use printfs, okay, and say, okay, the motor is currently at this speed, and the displacement is over here, and we are still ramping up, and so on. So it's easier to debug the program. Most students did that. Everything worked. But when they ported the program to an embedded controller, like an Arduino board, it stopped working. It's like mysterious, okay? But it worked here, but it doesn't work over here. And the reason was, when they were developing the program on the PC, an int has 32 bits. It's a 32-bit wide integer, which means if it is unsigned, you can represent values from 0 to a little bit more than 4 billion. But when you transition the program to an Arduino, an int, same thing, right? Same type, int, just int, or unsigned int in this case. An int only has 16 bits, which means now you can only represent values from 0 to a little more than 65,000. So the range is considerably less compared to a 32-bit platform, and as a result, the variables ran out of range, and as a result, the program stopped working. It compiled exactly, just fine, except it doesn't work. So the width of an integer is really important. You may not be used to this line of thinking, but every time you declare a variable as an int or unsigned or a char, you really want to make sure that your code will not exceed the range of whatever that integer allows you to use. Okay, so it's a consideration. Most people don't think of it because we are used to thinking, oh, integers are just integers. We have an infinite number of integers, but that is not the case. So now we can move on to the next one. So, however, an alternative to look at this is 19 has the same representation as 3 as a 4-bit number, as a 4-bit integer, unsigned. This is based on the congruent modulo between 3 and 16, and you can visit this Wikipedia page for a more complete treatment of this subject matter. So I am giving you the definition. So we can say that A and B are congruent modulo n when, this is one way to refer to that. This is my short, lazier version. But what that means, okay, so both of these are just representations. Both of these are notations. But what the notation is telling you is this part over here. So we'll take a look at this, with a little bit more explanation. This is a conjunction, so that means both sides of the conjunction should be true in order for A and B to be said to be congruent modulo n. But what does that mean? Well, what it means is you have to find the value of v, and v has to be an integer that is greater than or equal to 0, but less than n. Now, what is n exactly? We don't really care at this point. We just know that n is a positive integer that is at least 2. That's all we need to know about n at this point. All right, so we know b is somewhere between 0 and n, but excluding n itself. What about ka and kb? They're just integers. So ka can be -5 and kb can be 6. It doesn't matter. They just need to be integers. We already know what n is. N is the modulo system. And an a is really just v plus a certain multiplier times n. B is kind of the same thing, except the multipliers are different. They can be different. So as long as a and b as integers satisfy this requirement here, given what n is and given what b is, then a and b are said to be congruent modulo n. That sounds pretty abstract, right? So let's go ahead and talk about some examples. So the example here is, what about 3 and 19 when n is 16? So when when we are talking about 3, and basically v is 3 because v is also less than 16 in this case and greater than or equal to 0. So v is 3. So Ka is 0, Kb is 1. And that's why, since we can find a Ka and a Kb to make this conjunction work, that's why we can say 3 and 19 are congruent modulo 16. Are there any questions about the concept of congruent modulo sum n?
Yeah.
Question?
Yeah, I have a question. It's not quite totally clear, but
Okay, let me give you an example, a visual example. I think that should clear up, most of the questions. So give me a chance to switch to Zernal, because this one is going to be fun, because I'll be drawing something. And here we go. All right, so one way to look at this is to think of a circle. Okay? And on the circle, we have, 0, 1, 2, 3, 4, 5. And this is basically assuming n equals to 6, which is not from our example. Okay? So v can be any one of these 6 labels. So v has to be one of these 6. It has to be 0, 1, 2, 3, 4, 5, or, yeah, exactly, okay, because 6 is not one of the options. So now the question is, okay, so let's just say I choose v to be 4, okay? So what numbers would be congruent modulo 6 in this case? So basically what we have done is we say, let's just focus on this spot over here. And then we are basically saying, if you do a full rotation and keep counting up, or if you do a full rotation the other way, which is counterclockwise, and keep counting down, as long as you end up here, those numbers or those values would be congruent modulo 6. Let's try an example, okay? So let's try a clockwise rotation. So if we could do this part is a little harder because I have to use the mouse pointer to show you, what we are looking at. Then I cannot write at the same time. So this is 4, right? So let's do two full rotations clockwise and see what value is going to end up at the red spot over here. This is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm going to say, okay, let's probably don't want to use red here. So let's say A is 16. Now let's try to rotate it backwards, okay, counterclockwise. One full revolution, starting with the red dot here. Let's go ahead and give it a try. It just need to move my mouse pointer here. So we have 4, 3, 2, 1, 0, -1, -2. So now I can go back and say, okay, so let's b equal to -2. So now I can say A and B, which is 16 and -2, are congruent modulo 6. Why? Because both can be expressed in this format. 16 turns out to be 4. -2 is also 4. But we have to add a different multiple of 6 to 4 to get to these two values. With A, we have 2 times 6 because n is 6. And then with the other one, we have -1 times 6. So that is the reason, because A and B can be expressed in this format. They share the same V. They just have a different multiplier to n. And as a result, now we can say A and B, which are 16 and negative 2 in this case, to be congruent modulo 6. Yes, go ahead.
Is 10 also congruent modulo 6?
Yes. Yep, because 10 can also be expressed as 4 times a multiple of 6. And obviously 4 itself is also congruent modulo with 16 to negative 2 as well as 10. Is that okay? Are we good? Mm-hmm. So why do we want to deal with a math concept like this in a computer science class? Well, the first answer to that question is computer science is a branch of math. As much as some of us do not want that to be the case, it is. Okay, so we have talked about that already. But the question is really about negative numbers. In other words, can we use this kind of math to handle negative numbers? And the answer turns out to be yes. So skipping, all of this stuff here, we're going to skip to this table. This table is going to be useful later on as well in the lab. I'm just going to give you a little heads up. Okay. So in this table, we are basically looking at the value of V. We are fixing K of A to be 0 for the first column. So this column here is basically saying, what if K of A is 0, knowing that V is 0, 1, 2, all the way to 15. And we also know that N equals to 16, excuse me. So N is 16 in this case. Then we end up with these values of A, because this is V times 0 times 16. Well, that's just 0. This is 1 times 0 times 16, which is 1. So this is easy to figure out. So the column for A is pretty easy to figure out because we are not really adding anything to the values of V that we have listed over here. So are we okay so far with what the column of V is representing? That we have chosen K of A to be 0 in order to compute what is A going to be when K of A is 0 when B is the designated V on a particular row of this table. So are we good with so far? Okay. So the other two columns one is really kind of not really useful, but I'm going to put it here anyway, is what if K of B is negative 1? Okay, it's not a big deal. It simply means the multiplier of 16 is negative 1 in this case. But if that was the case, what would be the value of B? So on the first row, it's going to be 0 plus negative 1 times 16. So we have negative 16. And you can see how it progressed all the way to the last one, which is 0 times, this is 15, sorry. This is 15 plus negative 1 times 16, and that ends up to be negative 1. So do we know how to read this table, what it is trying to show you? It's just working out all the possible values of A and B. Once we fix N to be 16, and in one column we fix K of A to be 0, in another column we fix K of B to be negative 1. It's just enumerating all the possible cases. Are we good so far? All right. So what I'm going to do now is I'm going to take this table, put it into Zernal, because I have something that I need to show you more interactively. So let me go ahead and do that. And this is a really nifty tool. It is a screenshot tool. And now I can copy it to the clipboard. And then I can put it into Zernal. Let me do the Zernal trick here. And we want to do a paste. There we go. And I want to make sure that I do have the entire table. Yep, we do. Okay, excellent. All right, so what I'm going to do next is to say, we'll just look at B, and we ask what kind of binary number is going to represent B on each and every single row. Okay, this is going to be boring, okay, because we are just incrementing the binary number as we go. This is 0, 0, 0, 0. Can anyone argue that 0, 0, 0, 0 is the representation of 0 as a value? That seems to make sense, right? Okay. So the next one is just 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and then the 8 is 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and finally we have 1, 1, 1, 1. And I'm just going to say base 2 of V. Are we okay so far with this table? Okay.
Why skip 7?
Did I? It's just not lined up.
Oh, okay.
Yeah, 7 is just not lined up because at one point of time, I just started to drift like that. There we go. Okay, I hope this helps. Okay. All right, so when we look at this table, it seems to suggest that, I'll just randomly pick one. It seems to suggest that 1010 can represent 10, but it can also represent -6. It's the same bit pattern, right? But by using a different constant, a different multiplier of 16, we can now say, if the multiplier is a 0, it means 10. But if the multiplier is -1, it means -6. That is the trick. This is our ticket to be able to represent negative values using only zeros and ones. Okay? Do we have any questions about the statement?
So you're saying the bit in the front is going to represent whether the number is negative or not?
Aha, that is a very good observation. That's the next thing that I wanted to talk about. That's a very good observation. It is a pattern. Well, not quite, right? Because it depends on, because if you look at -10, okay, so this is -10 right here, and the bit pattern of -10 does not have a 1 as the leftmost digit. So now we have to say, if we are looking at unsigned integers, what would be the range that we are looking at? So I'm just going to use the blue color here to indicate. I'm going to use light blue. So these are the values that you can use when you're using a 4-bit unsigned integer. So that part is pretty easy. Okay, the light blue line, is something that we have already figured out in module 0282, which is when we talk about base 2 and other base conversion. But now the next question is, what if I want to look at a 4-bit integer as a signed integer? So now we have to make a careful choice because we cannot just use column B. Because if we, okay, let me just use a different color here. I'm going to use red here. So if we say this is how we interpret the bit pattern and these are the values that we can represent as a signed integer, then you have a little problem here. Because now signed integer cannot represent anything that is non-negative. That doesn't seem to make sense, right? I think we probably want a balance. Okay, we want a signed integer to be able to, one half of what it can represent to be non-negative, and then the other half to be negative. Does that make sense to you? That we do not want signed integers to only represent negative values. We want it to be able to represent both a little bit of some negative and some non-negative values. Does that make sense to you? And does it make sense to you that we want it to be like equal number? So instead of 2/3 being non-negative and 1/3 being negative, that doesn't seem to make sense. Half and half seems to make more sense, right? Okay. So I'm going to undo the red line or the red rectangle here. So can someone tell me if I want it to be a 50-50 split, okay, what would be the non-negative values that I want to represent? There are 16 altogether, so that means 1/2 is going to be 8. But which 8 non-negative values do you think I want to represent using a 4-bit number?
-8 to -1 to -8.
Non-negative, non-negative.
1 and 8.
To 1 to 8? Well, if you
0 to 7.
0 to 7, okay? Very good. Okay, so I'm going to use the red color pen here to basically say, okay, so for signed representation, we still want these ones, okay? Because these 8 values are representing values, which is exactly 1/2 of the 16 values that I can represent. Okay, so that seems to make sense. So what negative values do I want to represent as a signed 8-bit integer? It will be the other bit patterns, right? Because if I choose to represent 0 to 7, as 1/2 of a signed integer, those bit patterns are already used up. I cannot use the same bit patterns anymore. And I have exactly 8 bit patterns left for the negative values that I want to represent. So those 8 bit patterns would correspond to these values, -8 to -1. So once again, the light blue line is representing the range of an unsigned integer, given that it has a width of 4 bits. The red circles or the red rectangles are representing what values we can represent if we choose to look at the 4-bit bit pattern as a signed integer. Is that okay so far? Are there any questions? Okay. So you can probably imagine if this table is not about 4-bit integers, but it's about, let's say, 16-bit integers, it still works out the same way. The structure would still be the same. It's just that the range would be different. So can I move back to the notes? Because all of this is getting recorded. I'm double checking and making sure. All right, so we're going to move back to the notes. So the notes actually has the same kind of discussion, except it's in a written form, but it also gives you the equation of the range of values that we can use. So generally speaking, given a W-bit integer, which means we have W binary digits in a particular integer, the range of unsigned value is 0 to 2 to the power of W minus 1. We talked about that already, so this is nothing new. But the next sentence says the range of int, which is a signed integer, is going to range from -2 to the power of W minus 1 as a whole to 2 to the power of W minus 1 as a whole, and then the whole thing minus 1. That minus 1 is because of 0. 0 is one of the non-negative values. So are we okay so far? So given this is the equation, what is the most negative value that I can represent with a char? Remember, a char is nothing more than an 8-bit signed integer. So in that case, what would be the most negative value that I can represent?
-8.
No, it would be -2 to the power of 8 minus 1.
-64.
Close.
255.
No, it has to be negative. I asked about the most negative value. Okay. What is W again? 8. And that would be 7. And that would be
2 to the power of 7.
yes, but what is that? Okay, okay, yes, in this class you probably still need to pull out the calculator, but I think once you have like 30, 40 years of your programming under your belt, you go like 128. Yeah. So this is 128, and now we have -128. -128 turns out to be the most negative value that you can represent with a char. Okay? What about the other side? What about this thing here? Do you guys have to pull out a calculator to do all the calculations again? No. 127, because we already know this is 128, so this has to be 127. So I can make all of these claims all day long, but how do you check that that really is the case? You write a program, okay? So you write a program using a char type, and you assign negative 128 to that particular variable, and you say minus minus. And you see what happens. Because if you go minus minus, according to the wheel, where is it going to go? It's going to go back to the most positive value. And you can do the exercise the other way around, okay? You can initialize the variable to the most positive value, add 1 to it, and see what it is going to report back as.
Is that called overflow?
Hmm?
Is that called overflow?
Nope, it is not an overflow. Well, yes and no. It is, yes, it's an overflow, but it is not a concept that we have talked about yet. And it is not an overflow from the perspective of programming. Because C and C++ does not raise an exception when you cross that boundary.
Right. It just lets it go.
Oh yeah, C will let a lot of dangerous things go. Yep, it just won't tell you about it until it's way too late.
I had a potato in my first C++ class, and I almost burned it trying to run a program that ran infinitely.
Was it, did it involve just adding 1 to something
No,
until?
it was like something to the power of n.
Oh,
So
okay.
it had multiple, and then it was just like, I didn't notice it, but then my battery started to get really hot, or the bottom of it started to get really hot. I don't
Yeah.
have that laptop anymore.
Okay. So if you guys are interested, this is my ADHD talking. If you guys are interested, you can look up AMD motherboard explosion on YouTube. Yeah, somebody was running a benchmark test on an open, motherboard with a heatsink on the AMD processor, and then, in the middle of the whole benchmark test, that person decided to just lift the heatsink. It wasn't locked down. It was just, just on it, using gravity. So the person just going to, remove the heatsink from the processor. So you would think the processor would just kind of smoke, and die, right? No, it was much more spectacular than that. It exploded. Now, you would say, okay, so it just exploded this way, so it shattered itself into tiny little pieces. That would be like, yeah, that's kind of what we expected. No, that's not actually what happened. It blew a hole under. It blew a hole through the motherboard and the table under the motherboard. It became a little shape charge. Look up that word too, okay? But make sure that it's not traceable back to your identity when you look up that word, shape charge. Yes. It became a shape charge. It blew a hole through the motherboard, through the table. Yeah. So anyway, that's my ADHD talking because, it just goes like, hey, I know about this. Let me tell you all about it. All righty. So getting back to this stuff here. So assuming W is 4, resulting in N equals to 2 to the power of W, which is 16, and convert all the A values in range of int, So this is basically what we have talked about already. So what we have not talked about and what you have noticed earlier, let me switch back to the diagram, was there's something about all the negative values when you look at the bit pattern. Because remember, now that we are looking at a 4-bit signed integer, which means we are focusing on, these are the negative values that can be represented. So if you look at the binary representation of the negative values, there's one thing that you noticed earlier. Can you repeat what you noticed earlier?
The front bit is different.
The leftmost bit, which is also known as the most significant bit, they're all ones. Let me point out what we are talking about here. And this time I'm going to use orange. There we go. So we are talking about these bits over here. We notice that when this bit is 1, we are representing negative values. But when that bit is a 0, we are representing non-negative values. And that is applicable only when we choose to look at the 4-bit bit pattern as a signed integer. If we choose to look at it as an unsigned integer, that doesn't really matter. So what would be a good alias for this particular bit? In addition to the leftmost bit or the most significant bit, what would be another alias that is appropriately named after the meaning of this particular bit. It is called, I can tell how many people read ahead of the class, it's called the sign bit. Okay, the most significant bit is also called the sign bit because that bit, it becomes a 1 if we choose to look at the bit pattern as a signed integer, and that bit is a 1 when we are representing negative values. That's why it's called the sign bit. All right. Any questions up to this point? Nope. Okay. So let's move on, continue. All right. So now we have used the basic math, to kind of figure out a way to represent negative values. So what we have next is how do we perform arithmetic negation in base 2? So negation is easy when you're dealing with a normal number, okay? Because I can just do this on the whiteboard because it's so simple. If I give you a value in base 10 like 65 and I ask you, what is the arithmetic negation of 65? You go like, negative 65? Yep, you'll be correct, okay? That's easy. But that's because from our perspective, from the human perspective, this notation here is telling us it is the negative side of whatever is after that, right? So to us, it's easy. When all you have are zeros and ones, it's a little bit different because now you cannot just say, I'm going to put a sign next to it and say this is all negative. That doesn't work anymore, okay? So arithmetic negation turns out to be a little bit of an exercise. So we'll go ahead and I'm going to read this step by step and see if you guys can make the connection to some of the concepts that you have learned earlier in today's class and also some other concepts that you have learned earlier in the semester. All right, so we'll start with this, okay? Would anyone argue that, for v being a value between 0 and n, but excluding n itself, would anyone argue that negative v is congruent modulo n with negative v plus some multiple of n? Remember what the multiple of n is doing? It's basically doing a full revolution on the wheel, still ending on the same spot. Okay, and any value that land on that spot is considered to be congruent modulo n with all of the other numbers that land on the same spot. So I think this one is somewhat obvious, okay? Somewhat obvious. Well, that said, let's consider a much more specific case when k equals to 1, then negative v congruent modulo n with negative v plus n, and this expression here equals to negative v plus n minus 1 plus 1, which is the same thing as n minus 1 minus v, and then the whole thing plus 1. So my watch is reminding me to take row, so let's take row first, because this will take a little bit of time to explain. So I'm going to take row, and that is done with F1, and I just need to go to, oh, wrong class. That's okay, I can navigate to the class. Today. All right, and I set up the date already. I just need to let you know of the answer. Right here. Okay, so the name is going to be 20220914. And let me set up the due time or due date and also show you the answer. So I'll show you the answer first. The answer is, I just worked on this today and I cannot remember, it's tilde. Tilde. Okay, so the answer is TILDE, all lowercase. And there's a reason why I choose to use this word, and that will be explained in just a little bit. Okay, I'll give you guys until, plenty of time, okay? All right, so you have like half an hour to do this. That should be enough. All right. So as you guys are doing this, I'm going to switch back to the notes. So are we all done? Does anyone need more time for this activity? Okay. All right. So if you look at this from the algebra perspective, I'm really talking about from here all the way to here. Are there any questions about the algebra of y minus v plus n can be rewritten as n minus 1 the whole thing minus v the whole thing plus 1? You might have a question of why do we do something silly like that, right? But you probably do not have a question of the equivalency between the expressions. Because the plus 1 and the minus 1, they cancel out, right? So we still end up with really just a plus n and a subtraction of v on both sides. Are we good so far? So obviously the next question that I want to answer, that I need to answer, is why do we do something like that? That looks just kind of stupid. Why do we want to subtract 1 first and then add 1 back later on? What does that mean? So to explain that, we're going to have a restriction now. So instead of saying n can be any integer that is greater than or equal to 2, we're going to say n is a power of 2 now. So n can be 2, can be 4, can be 8, can be 16, can be 32, 64, 128, 256, 512, 1024, blah, 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 and so on. Because when n is a power of 2, something strange happens. So when n equals to 2 to the power of w, then we change the original expression, and basically we just look at everywhere that we have n, and change that n to 2 to the power of w, 2 to the power of w, and so on. So the first thing is, as it turns out, the binary representation of 2 to the power of w minus 1 is noteworthy. All right? So we'll go ahead and look at a few first, and then you guys tell me whether it is significant or not. Let's look at w being 2, okay? So when w is 2, what is 2 to the power of w, the whole thing minus 1? You guys can do this. 2 to the power of 2 is 4. 4 minus 1 is 3. All right. What is the binary representation of 3? In other words, what is it in base 2?
1, 1.
It's 1, 1? Very good. Okay, so it is indeed 1, 1. Let's step up the game a little bit. What if w is 5? 2 to the power of 5 is
32.
32. 32 minus 1 is 31. And what does 31 look like as a binary number?
1, 1, 1, 1.
It's 1, 1, 1, 1, 1. 5 ones. Because you need a 16. After the 16, you need an 8. Then you need a 4. Then you need a 2. Then you need a 1. I'll have one more, but I don't need your answer. I just want you to think about it. What if n equals to, what if w equals to 8? Then we have 2 to the power of 8, which is 256, minus 1, which is 255. So now the question is, what does 255 look like as a binary number?
8 ones.
8 ones, very good. Wow, so that means, yeah, go ahead. Question? Oh, okay. All right, that's okay. So that means, when we look at something like this, in binary, it's a bunch of ones. You go like, okay, but What is significant about that, right? So let's take a look at subtraction again, binary subtraction. So let me switch to Zerno. So we basically look at this from a 4-bit perspective. So we are looking at one, oops, wrong color. So we are looking at 1111 minus, and we'll just say that this is some kind of random digit as y. So I'll still call this one just y3, y2, y1, and y0. So typically we have a Q and a T column, and then finally we have a D. But this time I'm not going to refer to those things as those because we can actually figure this out pretty easily. First of all, in general, okay, I'm just asking in general, what is 1 minus a binary digit? I don't want to use y, I don't want to use x either, so we'll just call it, I cannot use w, we'll call it z, okay? So what is 1 minus z? And we know that z is Boolean, it's either 0 or 1. And that subtraction, actually, let's not use subtraction, let's use exclusive OR, because that is how we figure out q, right? We use exclusive OR between x and y to figure out q, which is supposed to be right here. But this time I'm asking you a much more general question, which is what is one exclusive OR with z? Z is just a Boolean variable. It's either a 0 or 1. Well, you can try to reason this out intuitively, or you can just kind of look at the truth table, so you don't have to kind of worry too much about, am I getting the math right or not? Okay, so let's look at it from the truth table perspective. This is z. Z can only be 0 or 1. This is one exclusive OR with z. All right, so what is one exclusive OR with 0? 1, very good. And what about one exclusive OR with 1? 0. Huh. Look at this truth table here. Don't you think we have seen this before, but not in conjunction with, not related to exclusive OR? Isn't that the same thing as not z? Huh. Because not z ends up with exactly the same values. Oh, okay. So that means this is just the negation of y, 0, the negation of y1, the negation of y2, and the negation of y3. Okay, not too bad. Now we have to worry about all the borrow bits, right? Because in a normal base 2 subtraction, we have to say, oh, t of I plus 1 is the borrow of xiyi or the borrow of qiki. But in this case, we are lucky. We don't have to worry about that too much. Why is that the case? What happened to all the borrows? Okay, that's a good starting point. Because 1 minus whatever cannot end up with a borrow. Okay? And because we are subtracting a 0 to begin with, so that cannot end up with a borrow of 1 either. Does that make sense? 1 minus whatever y0 is, cannot possibly end up with a borrow of 1. Because 1 is not less than 1, which is the maximum of what y0 can be. Okay. So not y0 can be a 1 or a 0, but that doesn't matter either because we are subtracting 0 from it, which also cannot end up with a borrow of 1. Is that okay? So that means whatever goes here has to be a 0. Does that make sense? This should help you connect concepts that we have learned before, because I'm just reusing how to compute t of I plus 1 in order to figure out this one has to be a 0. So what do we do next? We're trying to figure out the next one over here. But then you guys go like, it's the same scenario. 1 minus y1 cannot possibly have a borrow of 1. And then whatever not y1 is, because we are subtracting 0 from it, we can also not end up with a borrow of 1 either. So that means the next one up, which is t of 2, also has to be a 0. This one also has to be a 0. This one also has to be a 0. Guaranteed. Is that okay? All right, but we still have to figure out what is not y0 exclusive OR with 0. So now we use another truth table. So we say, okay, let's figure out this, okay? Z can be, so this time we are looking at Z exclusive OR with 0. So now we say Z exclusive OR with 0. So what is 0 exclusive OR with 0?
0.
That's 0. What is 1 exclusive OR with 0? 1. Okay. So that means we just have Z itself. This operation doesn't do anything. Exclusive OR with 0 does not do a single thing at all. Right? So that means using that, we now know that, oh, this is just the negation of y0. This is the negation of y1. This is the negation of y2. This is the negation of y3. Does that make sense to you? So what looks like a subtraction is not really a subtraction anymore. It's just a bitwise not. In C and C++, there is an operator for bitwise not. And what do you think that is? The whiteboard still has it.
Title,
Tilde.
tilde.
Yep. Tilde. And what symbol on the keyboard is tilde? The squiggly, exactly. So it is shift back tick at the upper right left-hand corner on the keyboard. That is the bitwise not operator. Yep. Okay. So that is why we want to subtract 1 from a power of 2 so that we end up with something that is all ones. So when we perform the subtraction doesn't have to be a formal subtraction. It is just a matter of negating all the bits. Okay? If it was a 0, it becomes a 1. If it was a 1, it becomes a 0. Are we good so far? So let me get back to the notes so that you know the context of this entire discussion. So the context of this entire discussion, so I basically use this chunk here to show that, the borrow bits, they all have to be zeros. And after the entire thing, we basically just end up, concluding that we are just negating y in this case, and ending up with this notation. So the distance, it's not the distance, the difference, the entire d row is just basically the bitwise not of the entire y row. Okay, if y is 0, you basically say d0 is not y0, d1 is not y1, and so on. All right? Okay, so that basically takes care of, let me go back to the original equation here. That means this entire portion is just the bitwise not of v. And then we add 1 to the bitwise not of v, and we call that arithmetic negation in base 2. So let me go through some more definitions, and then we have time to go through a few examples. So now we can plug this. What this means is it's referring to d is really the negation of y into the original congruent modulo end statement. So now it becomes the bitwise not of v plus 1. And that's also why I chose to use tilde as the name for today's bro-taking activity. So this is called 2's complement because 1's complement, I use C1 here, is basically just a bitwise not. So bitwise not is also known as 1's complement. And then we want to add 1 to that. That becomes 2's complement. So the term 2's complement comes from it is 1's complement plus 1. Are we still doing okay so far with all this stuff here? All right, so now we can go through a few examples. Okay, I have an example of using 3 but let's choose something else because I want to work on something different. So you guys can choose any either negative value from -1 to -7, or choose any non-negative value from 0 to 7. Pick one of those things. So the only value that we cannot use is -8. But anything else, pick one and I'll work on it.
+5.
Okay, so remember what you want to work on, and then we'll work on that next. Negative,
I said
positive,
+5.
+5. Okay. So we'll work with +5. So let's go to Zernal, and we'll work with +5. Time for a new page. All right, so we're working with 5. As a 4-bit number, 5 is 0101 in base 2. So when we want to find out how -5 is represented, it is the same thing as applying 2's complement to the same bit pattern that represents 5. So are we good so far? Because in what we see as a arithmetic negation operator is translating to 2's complement when it comes down to binary numbers. So now we work on this. This is the 1's complement of the same bit pattern plus 1. 1's complement is nothing more than just converting all the zeros to 1's and all the 1's into zeros. So now we have 1 0 1 0 in base 2 plus 1. And what would that be? Come on, you guys can do this. 1 0 1 0 plus 1, regardless of the base, is 1 0 1 1. Thank you. Okay. Remember that table that we looked at earlier? We can look it up and kind of cheat and find whether this is the answer or not. Yep, go ahead.
What's the little 2 doing hanging out there?
Oh, that's just emphasizing that we're dealing with base 2.
Okay.
Yep. A subscript of 2 means it is in base 2. All right? But before we go back and cheat and look up that table, let's just perform, because if I claim that 1 0 1 1 in base 2 is the representation of -5, what do you think I should get back if I apply 2's complement to 1 0 1 1 in base 2? Let me repeat the question. If I claim that -5 is represented by 1 0 1 1 in base 2, or at least it is congruent modulo 16, okay? That these two are congruent modulo 16. So let me just kind of emphasize that. There we go. So now the question is, what if I were to perform a 2's complement on 1 0 1 1 in base 2? What should I get back?
0 1 0
0 1 0 1, which is supposed to represent 5. Okay, so let's see if that works out. So now we ask, what is the negation of the 2's complement? What is the negation of 1 0 1 1 in base 2? And that would be the same thing as the 2's complement applied to 1 0 1 1 in base 2, which is the 1's complement of 1 0 1 1 in base 2 plus 1. And that would be what? What is the 1's complement of 1 0 1 1? 0 1 0 0. Very good. We just flipped all the 1's and the 0's. So we have 0 1 0 0 in base 2 plus 1, and that would be 0 1 0 1. Okay, so that seems to work out. But remember I said earlier that we could have cheated a little bit. That's because we have that whole table worked out already. So if I go back to this table, you can see, okay, let me get my cursor back up here. You can see how -5 has the representation of 1 0 1 1. So everything is consistent, right? This is all good. Okay, let me give you one that is kind of difficult to work with. And you guys would kind of frown on this one and go like, I'm not sure, but why you didn't tell us about this? All right, so we'll go ahead and take the 2's complement of 0, 0, 0, 0 in base 2. In other words, what is the arithmetic negation of 0? You guys are going like, well, it is 0 itself, right? But we want to double check, okay? Make sure that is the case. So this is now C1 of 0, 0, 0, 0 in base 2 plus 1, which is 1, 1, 1, 1 in base 2 plus 1. And tax says this is 0, 0, 0 in base 2. You guys go like, what? Why?
Is there another digit that goes to the carry one?
Exactly, because when we perform 4-bit operations, it means the result has to be a 4-bit result. So when we add 1, 1, 1, 1 and 0, 0, 0, 1, the sum is just 0, 0, 0, 0 with a K4 of 1. But that K4 is hanging out all by itself. It is not considered a part of the sum. So that's exactly what it means. Okay? So I can see you're making a connection between the carry look ahead adder lab, which has K3 kind of hanging out all by itself, and then the sum has the same width as X and Y. So now we can start to see all of those connections because everything is connected. All right, so this works out. Very nice. Now, if you guys are starting to have a nagging, question in your mind, and go like, but if we look at, just -3 and 13, let me show the table first, and then we'll get back to this slide. So if I look up the table, I'm just using this as an example. So it's not the only one, but it is one example. And you look up the bit pattern of 1, 1, 0, 1. It can represent 13 if we choose to look at it as an unsigned integer, but it can also represent -3 if we choose to look at it as a signed integer. So obviously the next question that some of you might have in your mind is, what is it then? Well, okay, the first thing, the answer is, what I usually answer people with is, it depends. So Tech, do you think sushi is a good idea today? It depends. So what does it depend on, right? The next paragraph is something that some of you may understand and some of you is going like, I have no idea what you're talking about. So what 1101 is representing, it depends on how the bit pattern is used. What are you using 1101 for? So in the case of the content of the video RAM of a monochrome display card, you can ask your grandparents about IBM PC computers with a monochrome display card because it's that old, circa 1981. Okay? But in this context, 1101, the first two, the most significant ones, means full brightness pixel. So it will be one single dot on the monochrome screen that is at 100% intensity. The 0, 1 next to it is going to be another pixel, and I mistakenly said it's going to be 2/3 of full brightness when it is actually supposed to be 1/3 of full brightness. But nonetheless, okay, you're basically specifying 2 pixels on the screen. One is at full brightness, the other one is at 1/3 of full brightness. It's not even a value. It's just 2 dots on the screen. But that's what 1101 is representing when this content is part of the video RAM of a monochrome display card. How many people know what is a dot matrix printer? Once again, your grandparents may know. Okay, so with a dot matrix printer, it's a very easy mechanism. It's a print head that has needles that can be actuated by electromagnets. So each needle can basically extend or not extend on its own. And that's how people used to print stuff. they have a ribbon, and then the print head would just basically go across, using it horizontally going across. And as it goes across, the needles would basically actuate when we want dots on the piece of paper. Is that okay? Do you guys have a general idea of what a dot matrix printer looks like?
Is it that one that's like really loud that goes?
Yep.
Holes on the side?
Yeah,
Holes on the
old
side, rip it.
school.
Yep, and those are called form-fed paper. Fan-folded paper. So you can basically buy an entire stack, like 1,000 pages, and it can keep going and going. You don't need a paper feed mechanism.
Sometimes with that.
Yep, and they're loud. Yes, they're loud, but they can be musical. Depending on what you're printing, they can be musical. They can actually play certain tunes. If you look up dot matrix printers music, I'm pretty sure you can find something. Again, ADHD talking. So, but in that case, it simply means we have two dots and then no dot and another dot arranged in a vertical manner. How can that be a number? It's not even a number, okay? It's just what dots appears on a piece of paper. So I'm hoping I'm illustrating that 1101 or any bit pattern has no inherent meaning whatsoever. It is only when you use it, then you have to decide what is it representing. Because it can mean two dots, one full intensity, one at 1/3 intensity on the screen. It can mean two dot and no dot and one more dot on a piece of paper. But it can also mean 13. It can also mean -3. So now the question is, when do we look at it as a 13 and when do we look at it as a -3? So to illustrate it, I'm going to switch to Joplin, and I'll give you the code of two C programs. Okay. The first one says main. Okay. And it says int x. So I'm assuming int is 4-bit wide in this case, so you just kind of bear with me. So we say x equals to, there are two variables, x and y. So we have x being -3, y being 0. And we say if x is less than y, C out x is less than y. All right, so if I were to run this program, do you think it's going to print x is less than y at standard output? I would think so. I mean, -3 is less than 0. I'll give you a second program. In the second program, instead of int xy, I say unsigned xy. Now remember, I'm dealing with 4-bit integers. So both the int and the unsigned are specifying 4-bit integers. The first thing you look at this, when you look at this program, the first thing is, isn't the compiler supposed to complain about x being unsigned and yet you're giving it a negative value? It depends on the compiler. Most compilers actually won't complain at all, because the -3 is just specifying what bit pattern should x be initialized to. -3, yes, go ahead. Oh. So -3 has a representation of 1101 as a binary bit pattern. That's what x is going to get. It's going to get exactly the same bit pattern as the program above. So both of these initialization, x ends up with a pattern of 1101. Now y is going to be the same because whether it's assigned or not doesn't really matter when it comes to 0. What does matter is, what about the comparison if x is less than y? This time, because x is unsigned, the code that your C compiler generates is going to say, with this comparison, we want to do a unsigned comparison. In other words, now x is forced to be interpreted as an unsigned integer, and therefore it is representing a value of 13. So now the question is really boiling down to, is 13 less than 0? The answer is no. So that means there's no output from the second program. The first program does tell you that x is less than y, the second program does not. But when you look at the actual bit pattern of x as a 4-bit variable, it is identical between the two programs. So this is what I meant when I said, well, it has no inherent meaning until you use it. The use in these two programs is saying we need to compare. That is a use of the bit pattern. Are we good so far? All right. So perfect timing. So I'm going to release the lab for today. There are a bunch of questions. You just have to read the questions carefully. They should not be very difficult considering what we have gone over in today's class. So we'll go ahead. So I'm going to go ahead and work on that. You guys can go take a short break if you want to. And I'll write down the access code on the whiteboard in just a little bit.